Hello, pipeliner friends. Welcome back to Beyond Pipelines Series 104. We are going to see combined stresses in the pipeline and the code compliances. This is one of the very important part of pipeline design, which is required for the thickness selection. We are exploring the uh, hoop and longitudinal stress combinations in the pipeline and the code compliance for precise pipeline thickness calculation. It is recommended to watch pipeline 102 lecture for this, for the better understanding of this lecture. Because in that lecture, I have already explained very basic concepts about how the hoop stress and longitudinal stress is calculated in the pipe, and we are going to explore it further now with respect to the actual design requirement and the code compliance. We are going to consider ASME B31.4 and B31.8 code, emphasizing their global relevance. They are widely recognized and used in majority of the consulting firms across the globe, and therefore it's always better to follow them and see them first. And some other countries might have their own regional nuances influencing certain factors, most probably design factor or certain criteria. However, the fundamental concepts shall remain same. I believe these, after learning these lectures systematically, you will be able to develop, your own Excel spreadsheet. So this should provide you a robust framework for developing your own Excel spreadsheets for your companies or for your own business. It will definitely help you, and that is the ultimate aim, that you should be able to develop your own spreadsheets, solve the run the calculations, and estimate or evaluate the analyze the pipeline thickness. Let's see the hoop stress or radial stress in the pipeline first. As per ASME B31.8, uh, clause number is not that critical, because as the version of the code changes, the clause number may change, but I have just given for the reference for the time being. As we have already seen earlier in the basic conceptual lecture, pipeline 102, about the hoop stress, it is nothing but PD by 2T. Okay, and these FET are the additional factors which we need to see now. The F is nothing but the design factor, which I will elaborate in more details later how F is selected. But at the moment, for the time being, you consider F as a design factor, which is the most important thing, right? Because whenever we are doing any design for that matter, what we do is we always consider the strength of that material which we are designing, which we are going to manufacture it from, and we apply factor of safety such that even if it sees the maximum desired load or design load, then there should be some margin in its strength. So we will not be designing it exactly to the requirement of the design conditions or the applicable loads, but we'll always keep margin, so that in case of any uncertainty, in case of any undesired situation occurs and the load exceeds beyond the design value, then there should not be any catastrophic failure happening. So that is the reason of having applicable design factor. It's very important. E is a joint efficiency. In this case, our code covers joint efficiency provides as 1 if we are manufacturing the pipe in certain way. And for oil and gas industry, the pipe manufacturing and its welding and NDT techniques are very strictly followed. Therefore, our joint efficiency is always 1 for the oil and gas pipeline systems. Yeah, oil and gas pipes basically. T is temperature derating factor, which I have already explained in 102 pipeline 102 lecture. Once again, I will just try to quickly wrap it up. Whenever the temperature, which is going to be from the fluid service that the pipeline is going to handle, or sometimes the ambient condition, the if the pipe is exposed to uh, above ground outside sun, and then there will be black bulb temperature effect happening, the considering the black color of the body of the pipe body, it may keep on absorbing the sun radiation heat, and because of that its temperature will keep rising to maximum 82 degrees centigrade, which we call it as black bulb temperature. So with respect to the desired temperature, the design temperature or black bulb temperature, whichever is higher, the strength SMYs of the pipeline material is going to reduce, and this is called temperature derating factor, which is given in with respect to the temperatures. Now B31.8 says that up to 121 degrees centigrade, the derating temperature, derating factor can be considered as 1, and beyond that it becomes a bit difficult. Then we need to see the different codes and different practices, or maybe we need to do actual testing at the elevated temperature, tensile testing, to get the temperature derating factor if the temperature is going to be higher. Okay, so normally we don't encounter in oil and gas pipelines higher temperatures. So up to 121 degrees centigrade, it will be 1. Okay, so in F, E and T, E and T are going to be 1. So F will be the design factor, which is normally 0.72 or 0.6. And with respect to that, the PD upon 2T and into F into E into T. So 2TF will be the stress, or if we are calculating the thickness, then it will be PD by 2 times SMYs into design factor. This is how the thickness can be calculated. Okay, this, and then this is going to be the F is going to be the design factor. Okay, so let us move further. B31.4 is another code used for the liquid services. The one earlier which we saw was 31.8, which is used for the oil service, oil and gas services. Basically, oil normally when it is having unstabilized crude oil, which is having a lot of gas phase or multi-phase, prominently gas phase, then we apply B31.8. But when there is a stabilized oil or water or liquid services, then we use ASME B31.4. The basic criteria is the services which are covered under B31.4 are considered as less critical as compared to B31.8 services, and therefore you will find one difference. The formula, the basic concept of the hoop stress or the thickness is of course same, whether you use B31.8 or B31.4, and I've already mentioned that the same concept will be applicable globally. Okay, even though some localized changes can happen. So B31.4 also provides exactly the same formula as given by B31.8, PD by 2S or PD by 2T for the stress. Here you will be surprised that there is no F, E and T that was present in B31.8 criteria. Okay, why it is so? Because as I explained, B31.4 covers the relatively less critical services, fluid services. Therefore, they have standardized the design factor as 0.72. Okay, so SMYS for B31.4 or allowable stress under B31.4 will be considered always as 72% of the SMYS. Okay. So this is what is the fixed criteria given by B31.4, whereas the design factor remains variable in case of B31.8, where we apply it in a different methodology. There are certain criteria for that. In certain cases, the design factor is increased. In some cases, it can be reduced to minimum 0.72. So as I said, B31 point considers constant design factor of 0.72 irrespective of any location class. Location class and the design factor selection under for B31.8 we will see in a separate lecture. That itself is a quite a elaborative topic, so I need to explain that under one full lecture. Okay, let's move forward. Let's see the whenever pipeline is installed, it undergoes various types of longitudinal stresses also. We just saw the hoop stresses, but now we have to see the longitudinal stresses. And as we have seen the longitudinal stress, okay, the though the formula is PD by 40 hoop stress upon 2, but there can be different types of longitudinal stresses. What we saw PD by 40 formula is related to the longitudinal pressure stress, also called end cap effect, which we have seen in pipeline 102. So that is just one type of longitudinal stress acting in the pipeline, but there are other longitudinal stresses acting, which we need to study properly. So there will be longitudinal stress due to Poisson's effect. Okay, I will try to explain Poisson's effect. Then there will be stress due to pipeline laying or bending. Okay, so whenever you are going to lay the pipe, we are considering that pipeline is a long distance pipeline and it will be laid along the ground or buried. Then it will be following the profile of the ground from one point to other point as the pipeline length is going to travel. So what is going to happen is, because of this laying, the curvature of the land, okay, it might have different curvatures, or sometimes it can be just flat terrain, but sometimes the terrain can be curvature, having curves, like ups and downs and valleys and mountains. So the pipeline has to travel along that, and it has to take uh, the uh, localized gradient or localized curve of that, we'll say the land there, terrain available there, that may introduce some kind of a stress in the pipe. Okay, because pipe, if you try to imagine that it will have one elastic radius, so by that radius, if you try to bend the pipe or lay the pipe, it will not induce any stresses in the pipeline. But if your curvature or profile of the land or terrain is lower than the elastic radius of the pipe, and you are going to force the pipe to be in that particular radius and backfill it with the soil cover, there will be laying stresses acting in the pipe, which we need to limit them when we are calculating the combination of all these longitudinal stresses together, which is also called sometimes the net longitudinal stress. Then there will be, of course, thermal stress, which is definitely going to act in longitudinal direction, because pipe is going to expand in along the length, and there will be some restrictions from it to expand, so it will have the thermal stresses getting induced in that. To gain insight into these types of stresses, it is important to grasp various restraint zones encountered by the pipeline. So, as I said, the longitudinal pressure stress will act when there is a restraint, particular restraint for the pipeline to expand in against the pressure. Poisson is also one kind of a stress inducted on the pipeline due to the soil, okay, which is not allowing the pipe to extend itself due to the pressure in the longitudinal direction. Laying stress, as I said, is of course because of the along the length and related to bends. Thermal stress by default is when you bury the pipeline is trying to expand due to temperature. So when you say buried pipeline, means it is having restraint, okay, and it is not allowed to expand, and that is going to create thermal stress in the pipeline. So we have to study what are the different restraint zones encountered by the pipeline, because initially pipeline might be above ground for the pick trap and associated connections. Then it will be buried, and then after burial, after certain distance, again some restraints may change, which we have to study. And knowing them is very important to calculate the net longitudinal stress. And then the net longitudinal stress and hoop stress combination will be considered as the equivalent stress, which we need to evaluate to find out the suitable or adequate pipeline thickness. So this is how critical it is going to be. So let us study the restraint zones encountered by a buried pipeline. Why restraint zones are related to buried pipeline is because, when the pipeline gets buried, there will be a soil cover added on top of the trench on the pipe. So the soil weight of the soil will provide restraint or the resistance to the longitudinal movement of the pipe. It will be due to different reasons which we have seen. What are the different stresses it is encountering? So the soil is resisting all these longitudinal displacements of the pipeline. Okay, let's see a typical cross section of a pipeline. So this is the above ground pipeline first section. This is the point where it gets buried. Some distance along the when it gets buried, some distance along the trench where the soil weight is acting is called partially restrained zone. After some point, some length, some specific length, uh, the pipeline will become kind of a stable, in terms of the displacements. Along the length will almost become negligible, and that zone is called fully restrained zone of the pipeline. And a point at which this stability is achieved by the pipeline from partially restrained zone to fully restrained zone is called virtual anchor. So when you develop the Excel spreadsheet, you will understand, you can easily calculate the length, virtual anchor length from the burial point by doing the calculation, and that so it can be analyzed, and then it can be predicted by means of the calculation, and then we can, when we do the scissor stress analysis, we can always see that. Now let's see what are these restraint zones what we saw encountered by a buried pipeline. So first zone was unrestrained zone, as we saw. This is the above ground section of the pipeline, okay, unrestrained zone. This section of the pipeline experiences some restraint depending upon the flexibility. So what happens is, of the supports and line stops. So here there is going to be a pick trap which is having some supports, and it is going to the bar T will get connect the bypass piping with the on-plot piping network, piping work, which can be the station piping. So that piping will have some flexibility, and the line stops and guide supports, so the flexibility and such supports will determine the stresses that are going to act in the above ground section of the pipeline or unrestrained zone. So there are no soil loads acting, or soil resistance is not acting in this zone, but the resistance or stresses are induced by means of the configuration of the connected piping and the type of supports and the distance at which these supports are provided. So this is normally the interface with piping, and in the scissor model, when we do the combined model with pipeline along with the piping up to certain limit stops or anchor supports, we can analyze the stresses acting in the unrestrained zone in a better way. Now we'll go to fully restrained zone first, and then we will try to understand partially restrained zone. So fully restrained zone is nothing but a buried section of the pipeline, and this is a stable section, as I explained, where the soil weight is going to create the resistance to displacement of the pipeline. And when the soil weight See, soil weight is acting in the lateral direction, and there will be a friction acting between the pipe and the soil weight and the soil, yeah, between the pipe and soil. So, equivalent to the weight into that friction factor is going to be the axial force acting due to soil weight on the pipe surface. And when the stresses or the displacement of the pipe in the longitudinal direction, the stresses induced or forces acting for the displacement of the pipeline are going to match exactly with the friction factor into the weight of the soil. Yeah, then we can say that the soil weight is going to exactly balance the movement of the pipeline, and this is called fully restrained zone. So this means the pipeline is going to be in complete equilibrium or completely stable. So there will not be any displacement acting in this region of the pipeline. When we do scissor stress analysis using scissor software, we see that one particular virtual anchor point can be observed, at which the displacement that point onwards the displacement becomes zero. That means the fully restrained zone is attained by the pipeline. Partially restrained zone is, as I shown in the cross section, it is basically the intermediate zone between unrestrained to fully restrained. So this is where the length of the pipeline is relatively, as the length, I mean soil weight is acting, but from initially for certain distance, the weight of the soil cannot provide enough resisting force for the displacement of the pipe. As we go further, when the length of the trench or length of the pipeline go on increasing, then eventually the weight of the soil balances the uh, longitudinal displacement of the pipeline, which is fully restrained zone. But initially for certain distance, it cannot, the weight of the soil is not adequate to provide the complete full restrained zone, and that is called partially restrained zone. So that the transition point from where the partially restrained zone gets converted to fully restrained zone or the displacement becomes zero is, as I said, called virtual anchor point. So from virtual anchor point there will be some displacement observed towards the unrestrained zone. So these displacements gets towards the unrestrained zone, and normally the pick trap, you will find the pick trap which is connected at the end of the unrestrained zone of the pipeline, will be moving axially uh, away from the pipeline direction, okay, because the displacements are going to act from the virtual anchor point all the way up to the peak trap, which is end of the pipeline, or just the end of the start point of the unrestrained zone we can call it, or end of the pipeline, or start point of the pipeline, depending upon in which direction we are going. Okay, now let's see the stress combinations which are going to act in this various restrained zones. So first let us see the unrestrained segment or unrestrained zone. In this, the net longitudinal stress will be some of the following stresses. As we have seen, the unrestrained segment will be having end cap effect, or the longitudinal pressure stress will be acting, okay, because so that will be PD by 40, or hoop stress by 2, okay, which is called end cap effect. And this stress is going to act because there is a pressure acting. So it's a natural phenomena. Whenever any pipe is having internal pressure, there will be two stresses acting in the pipe. One is the hoop stress and one is the longitudinal pressure stress or end cap effect. So this is going to act. There will be bending stress, which is related to the support spans and bends and bending moment acting in this, okay, which is any above ground supported, pipe supported on the with the support span will encounter these stresses. Normally it's going to be negligible if we are providing adequate support span. Thermal stress, definitely the thermal displacement or thermal expansion is going to, or contraction is going to happen in this section of the pipe, but there will be limited resistance offered by only the associated bypass piping configuration and the supports provided, but not like the way buried soil is going to act and restrict the movement. So it's not going to happen in the unrestrained segment. So this will not see thermal stress. Okay, there will be some resistance from the piping, as I said, but it will be determined only by stress analysis program. Okay, when we do the combined modeling, so thermal stress won't be acting in this section. Now the unrestrained segment, okay, we have seen that the net longitudinal stress will be longitudinal pressure stress and bending stress combination, and then it has to be combined along with the hoop stress. Okay, this is the code requirement. So design code says that you have to take a combination of uh, longitudinal and radial or hoop stress together in a von Mises theorem. So there is a specific formula given in the code, and when you combine that, okay, there will be the combined stress, and then that has to be less than the code compliance provided, which we will see in the next slide. But for each segment or each restraint zone, there will be a combined stress calculated, which is a combination of hoop and the net longitudinal stress, and that will be compared with the code compliance. And if it is less than code compliance limit, then we can say that the selected thickness is adequate. Now let's see the fully restrained segment. Okay, fully restrained segment, as I said, will have net longitudinal stress due to following three reasons. First is Poisson stress, which is normally considered as 30% of hoop stress. So this 0.3 is called Poisson's ratio. So I will explain that. I will try to explain Poisson's stress or Poisson's theory in one of the short videos later. Okay, right now you just consider that whenever soil is restricting the movement of the pipe, then the Poisson stress of 30% of hoop stress is going to act in a longitudinal direction. Thermal stress, obviously, because pipe is trying to expand or contract, if the temperature is going to be lower than the ambient temperature or the soil temperature, because the line is buried inside the soil, so there will be thermal displacement, either expansion or contraction, that will be resisted by the soil weight. Soil is not going to allow that pipe to expand or contract, and that is definitely going to create a thermal stress. And there will be laying stress, which is equivalent to pipe laying bend radius. As I said, if the laying radius is lower than elastic bend radius of the pipe, then there will be some stresses induced, and which we can easily control by either providing the very large laying radius by doing the trenching configuration accordingly, or by means of providing the thickness margin to take care of this. Okay, which you can easily understand when you start developing the spreadsheet, which we can, I will explain one spreadsheet at later stage. Okay, but these are the basic concepts I want everyone to understand. So the combination of these three stresses, now you can easily understand that the Poisson stress, thermal stress and laying stress are going to act in different directions, because Poisson stress will be acting maybe against the thermal stress. Okay, when I explain the Poisson's theory, you will understand what I am saying, but Poisson stress is going to act against the thermal stress if the thermal stress is related to higher temperature and expansion of the pipeline. Okay, so Poisson and thermal are going to be like in acting in opposite direction, and laying stress will act in both the directions, because whenever you bend any pipe at the inside surface of the pipe, which is also called intrados, there will be compressive stresses, and when the outer surface of the bend pipe or extrados, there will be tensile stresses acting. Okay, so we have to consider the worst direction. So Poisson and thermal, when we balance each other, whatever is the dominating force, dominating stress, we add that direction of the additional magnitude of the laying stress, or that direction of the laying stress in that. So laying stress always gets added to the net sum of Poissons and thermal, which are acting in different directions. Then we will, so by doing this combination of A minus B minus C, or A minus B plus C, depending upon who is dominating, that will decide the net longitudinal stress. Okay, and then the net longitudinal stress is then combined with the hoop stress by a formula given in code, which is there are two theories for that: von Mises theory and Tresca theory, but we normally use von Mises theory. As per that, we do the combination of these stresses, and the combined stress has to be less than the code compliance. Okay, now let us see the partially restrained segment. So in partially restrained segment, which is from the transition point where the above ground pipeline gets buried to attaining the fully restrained zone, which is after the virtual anchor. So in that zone, there will be at one end the pipeline is going to encounter fully restrained zone, uh, which is on the right side, which is the buried point, and other end is going to see the unrestrained zone. Okay, so this partially restrained zone, uh, the code compliance is not covered in the code doesn't really consider partially restrained segment, but to calculate the virtual anchor length, we need to analyze this segment, and the stresses in this segment can be easily analyzed by means of the you know the by combining the unrestrained and fully restrained segment stresses together. So if you see the fully restrained segment, there will be certain stresses acting, and unrestrained segments will have the end cap effect, because bending will be just related to the support span. So let's neglect that. So end cap effect and the fully restrained will have the thermal and Poisson combination and the laying stress combination. So if you take a differential of these two stresses, net longitudinal stress acting in the partially restrained zone can be calculated. As I said, there is no even though we can do the combination and combined stresses can be calculated, but there is no code compliance given for that. Okay, so mainly these combined stresses will be calculated. They will be converted in the form of longitudinal force acting, and using that force we can calculate the virtual anchor length. We can predict the virtual anchor length at which the fully restrained zone can be attained by the pipeline. And once you develop the Excel spreadsheet, you will understand what I'm trying to say. And if you compare that with the results given by the stress analysis program, Caesar model, you will understand that around same length, around same similar kind of length, your Caesar program will also show you that the displacements are becoming zero. So fully restrained zone is getting achieved. So this will allow you to calculate the virtual anchor length, which we can develop later. So let's see the longitudinal stress combinations in the pipeline with respect to the code compliance given. So the ASME B31.4 and ASME B31.8 provides the code compliance, which is nothing but allowable stress limits for the net longitudinal stress and the combined stress. For the unrestrained section, the longitudinal stress shall be less than or equal to 75% of SMYs. Okay. The as I explained earlier, unrestrained section is also connected with piping or B31.3 code interface. So normally a stress analysis is done using a software like Caesar to carry out the entire configuration modeling with respect to the some section of the buried pipeline, above ground pipeline, the pick trap, associated pipe work, bypass piping, and the connected piping up to certain distance with respect to the anchor or line stop and guide supports provided, and the overall flexibility check is done, which is nothing but the combination of above ground and below ground stress analysis to determine the unrestrained section code compliance. Whereas for fully restrained section, we can always check the net longitudinal stress, and it has to be lower than 90% SMYs, and the combined stress, which is a combination of longitudinal and hoop stress. There are two theories involved in that. One is von Mises and one is Tresca, and normally von Mises theory is applicable. And once you calculate the combined stress by means of one of these theories, the formula is given in the code. Then the combined stress shall be less than 90% SMYs. So surprisingly here the net longitudinal stress also is limited by 90% SMYs, and combined stress is also limited by 90% SMYs. The main reason for that is the pipeline is buried, so it is continuously supported. So lower safety margin is considered as compared to the unrestrained section which is above ground. Hope you have understood the code compliance part of it. So it looks a bit tricky, but when you read the code with respect to this lecture, now your understanding will be much better and much simpler. Partially restrained zone which we have seen is not covered by the pipeline code, but it is just conceptually derived, and it is normally required for estimating the virtual anchor length, but not for the code compliance failure analysis. Okay, now let's see some other considerations. We have reached to the point that we can now calculate the thickness of the pipeline with respect to various segments, related hoop and net longitudinal, and the combination of hoop and longitudinal stresses. So this is the main pipeline thickness part, but we cannot neglect the other considerations which are to be also verified when we finalize our thickness. Let's quickly wrap up what are those points. So first one is vacuum condition. So we need to check the selected pipeline thickness based on our earlier criteria for vacuum condition, because sometimes pipeline can encounter vacuum conditions when there is a large elevation difference, the slope, or if the suction tanker is to be connected to the pipeline by means of a small connection provided on the pipe, it can encounter vacuum condition. So it is always designed for full vacuum condition. D by T ratio, it is nothing but the thickness of the pipe cannot be too low, because then pipe can become very flimsy and non-rigid, and then during the welding and installation and lifting of the pipe it can become impractical. So to make it sufficiently rigid pipe, the certain minimum thickness is ensured when selecting the pipeline thickness, and for that the guidance is given by keeping the D by T ratio maximum up to 96. So if you keep the D by T ratio less than 96, then definitely the thickness will be adequately provided for the rigidity purpose. Under thickness tolerance or mill tolerance, which is definitely used for the piping thickness calculations, but for the pipeline the design factor already takes care of the under thickness tolerance, and that is the reason I have specifically added it in this lecture. So there is slight difference in consideration when you are doing piping thickness calculation versus pipeline thickness calculation. And last but not the least is corrosion allowance, which is typically included to ensure extra layer of thickness, because the service fluid may have a corrosive effect on the selected pipe material, and it may corrode the pipe during the design life. So the corrosion and materials engineer, they will do the analysis and estimate the corrosion allowance required, okay, for ensuring that throughout the design life the pipeline will not corrode to such an extent that it cannot withstand the design pressure requirements anymore. So this corrosion allowance is added when you calculate the thickness based on various criteria we have considered so far, and when you arrive at the final thickness you add corrosion allowance on top of it, and then you order the pipe.
So friends, I'm sure this lecture on pipeline combined stresses or equivalent stresses would have helped you to understand the concepts better, and with this I'm sure you will be able to read the code when you open 31.4 or 8. Your understanding will be much better and faster. I explained you about the combined stresses as well as some additional factors while determining the pipeline thickness, like vacuum and under thickness tolerance and corrosion allowance, etc. I did not cover one factor which was related to bend thinning, which you should consider, and I will try to cover it in one of the short lectures in Beyond Pipeline series in future. But I'm sure with these concepts you will be excited to start developing your own Excel spreadsheet and start calculating the thickness values for your pipeline design. All the best to you, and see you in